Greetings, dear colleagues. My name is Sadykov Dinislam. I am a postgraduate student at ITMO University, and the topic of my report is the effect of increasing plasticity in high-strength ultrafine-grained aluminium copper zirconium alloy. Aluminium and aluminium-based alloys are widely used in various industries such as aerospace, automotive, shipbuilding, and electrical engineering due to the good combination of their characteristics. Aluminium is light, has high electrical conductivity, corrosion resistance, and is one of the most common elements on our planet. I would especially like to note the extremely high applicability in the electrical industry. According to some data, from 13 to 18% of all aluminium produced is used in this area. Therefore, nowadays a special attention is paid to developing electrotechnical or conductive alloys with outstanding properties. First of all, aluminium alloys are used in cables for air power lines. However, there is the key problem. This is low strength of aluminium and its alloys. Therefore, to create long wires, aluminium is reinforced by steel core. That leads to an increase in electrical resistance, an increase in the cost, and makes the constructions heavy. In this regard, in recent decades, in addition to standard alloying, the approach to create ultrafine-grained and non-crystalline structures by methods of severe plastic deformation has been increasingly used, since, in accordance with the Hall-Page relation, the grain refinement provides an increase in strength. Briefly, such approach is usually called as design of microstructure. Some results of applying the SPD processing are presented here. Obviously, the strength of UFG alloys is much higher than in the coarse-grained state, while maintaining a high level of electrical conductivity. However, another problem becomes apparent. SPD structuring leads not only to increase in strength, but also strongly reduces the ductility of UFG materials, which greatly limits the scope of their functional application. So, various industries are constantly in need of new types of aluminium alloys, which combine high strength, ductility, and, in the case of electrotechnical applications, good electrical conductivity. To achieve this goal, the selection of optimal alloying parameters and design of the microstructure are carried out. Form special UFG or NC structures have high strength and acceptable electrical conductivity, but usually low ductility. From here comes the task to search for methods of increasing ductility of UFG and NC materials while maintaining high strength and acceptable electrical conductivity. Recently, it was found that special additional deformation heat treatment, or just DHT, consisting of low temperature annealing plus additional small high pressure torsion deformation, provides significant increase in ductility of high pressure torsion processed aluminium while maintaining a high level of strength. Deformation-induced increase of ductility is not typical for coarse-grained metals. Theoretical model was proposed to explain this plastification effect, or just PE, in UFG aluminium. According to this model, during the additional deformation, an additional density of extrinsic grain boundary dislocation is introduced into the structure of high-angle grain boundaries, relaxed after annealing that leads to facilitating the emission of dislocation from grain boundaries. Then, a similar effect was found for aluminium-copper alloy structured by HPT method. The next step was to study the effect of similar deformation heat treatment on the physical and mechanical properties of the new perspective UFG aluminium-copper zirconium alloy. Zirconium was introduced to form metastable precipitates of the aluminium-3 zirconium phase to provide the thermal stability of the mechanical properties of the alloy at elevated temperatures. The chemical composition of the studying aluminium-copper zirconium alloy, for simplicity we'll call it just alloy, the method of its obtaining in the initial coarse-grained state, as well as the scheme and parameters of UFG structuring using the HPT methods are shown here. The initial coarse-grained state was obtained by the method of combined casting and rolling. Artificial aging at these parameters was carried out for homogenization and formation of precipitation of nano-sized metastable phase of aluminium-3 zirconium. The UFG structure was formed by high pressure torsion at room temperature. A part of the HPT processed specimens was annealed at various annealing parameters in order to study the effect of annealing on the physical and mechanical properties of the UFG alloy. Finally, after annealing, the effect of a small additional HPT deformation on the strength properties of the alloy was studied. Mechanical properties were measured by conducting unaxial tensile tests and microhardness measurements. The electrical conductivity was measured by the eddy current method. The study of the microstructure was carried out by various complementary methods. Conducting HPT led to a dramatically increase in strength characteristics. Tensile strength increased by 2.7 times and yield strength by 2.3 times compared with the state of AG, while maintaining a fairly high electrical conductivity. At the same time, as expected, the ductility strongly decreased to 3.5%. The transmission electron microscopy analysis of the microstructure of the alloy in the AG state showed that the average grain size is 630 nanometers. The presence of a significant number of precipitates of the aluminum-zirconium phase, located both along the grain boundaries with average size 35 nanometers and in grain interior with average size 9.3 nanometers, was revealed. The highest electrical conductivity of the studied alloy, 54.8% in Ajax, was achieved by purification of the aluminum matrix from solute alloying atoms in the process of artificial aging. HPT processing led to the formation of an UFG structure with an average grain size of 285 nanometers. The number of aluminum-free zirconium precipitates substantially decreased, however, the average size increased to 18 nanometers. The precipitates of aluminum-free zirconium predominantly located in the grain interior. That pointed to partial deformation-induced dissolution of these precipitates. At the grain boundaries, copper-containing precipitates, aluminium to copper phase with an average size of 20-40 nanometers, are clearly observed. Their belonging to the copper phase was confirmed by microdiffraction images and EDX analysis in STEM. In order to obtain optimal annealing parameters, the study of annealing kinetics was carried out. It was found that the best combination of microhardness and electrical conductivity is achieved after annealing at temperature of 125 degrees Celsius for 2-4 hours. This state was chosen for tensile test. As we can see, the state after additional annealing demonstrates still a good tensile strength, about 485 megapascal, but very low ductility, less than 2%. However, we found that on subsequent additional small HPT deformation by a quarter of a turn leads to a substantial increase in ductility, while the high level of strength is kept. Thus, we see that the proposed deformation heat treatment leads to a significant increase in ductility while maintaining high strength and reasonable electrical conductivity in the studied alloy. To better understand the observed phenomenon of increasing ductility by deformation, we studied microstructure of alloy after annealing and subsequent deformation. It was found in both states the grain size remained practically unchanged. At the grain boundaries there are still precipitates of the copper phase, the size of which increased to 60 nanometers. The main microstructure change is decrease in dislocation density after annealing and substantial increase of it after subsequent additional deformation. In this regard, the obtained effect of plasticization can be well described by the physical model proposed by us earlier for commercial pure aluminum. According to this model, plastic deformation in UFG aluminum structured by HPT is carried out by the emission of lattice dislocations from triple junctions. The low plasticity in the state after short-term low-temperature annealing is explained by a decrease in the grain boundaries dislocation density. As a consequence, an increased external stress is required for the emission of dislocations from grain boundaries, and a decreased number of lattice dislocations is emitted from grain boundaries. An increase in plasticity in the state after annealing and subsequent small deformation is associated with the introduction of an additional dislocation density in grain boundaries, which leads to an increase in the number of dislocations capable of forming pile-up under applied external load. In addition, it is worth noting that after DHT, the dislocation structure of the grain boundary itself may differ from that in the AG plus HPT state. That may affect the formation of pile-up of grain boundary dislocations under applied external stresses. However, it is known from the literature that some UFG aluminum alloys exhibit increased plasticity and even superplasticity in some cases due to the significant contribution of grain boundary sliding, or just GBS, to the total plastic deformation. Such intensification of GBS is usually associated with a rather large value of coefficient of strain rate sensitivity. In this regard, the influence of the strain rate on the observed effect of plasticization was investigated. Due to the fact that state after annealing showed an extremely low plasticity, less than 2%, the main attention was focused on states HPT and after DHT, with an increase in the strain rate and increase in strength characteristics is observed in both states. For the HPT state, the yield strength increased from 320 to 430 megapascal in the entire range of strain rates under study. The tensile strength first increased from 521 to 570 megapascal, then was kept on this level. Such behavior is typical also for the state after DHT, but the strength characteristics are somewhat lower in the whole range of strain rates. However, the strength of alloy after DHT remains high enough. After DHT, the alloy not only has high plasticity, approximately 11%, but also retains high values of plasticity in a wide range of strain rates, which indicates the stability of the plasticization effect in this strain rate range. With a further increase in the strain rate, the value of plasticity decreased to 5%. However, this value of plasticity is much higher than at a similar strain rate in the state after HPT, when the samples are fractured almost brittle. This suggests that the relative effect of plasticization manifests itself in the entire range of strain rates under study. The strain rate sensitivity coefficient, or just M, was determined for both investigated states of the alloy. It was found that the deformation heat treatment does not practically change the value of the coefficient M. Hence, it can be concluded that GBS doesn't play a key role in the observed effect of plasticization. The degrees of the effect of plasticization and its possible complete suppression at high strain rates can be explained within the framework of the model discussed above. It is known from the literature that the upper limit of the time required for the formation of dislocation pileups in grain boundaries at room temperature in the HPT processed aluminum is about 6 seconds. Such time is already comparable with the time needed to reach the yield stress and the strain rate of 10 to the power of -2 reciprocal second. In this case, grain boundary dislocations simply do not have enough time to form sufficiently powerful pileups in grain boundaries, which leads to lower plasticity and even suppression of the plasticization effect at higher strain rates. Summarizing my talk, a comprehensive study of the influence of structuring of aluminum copper zirconium alloy by the HPT processing on the strength, ductility, and electrical conductivity has been carried out. It was shown that HPT treatment leads to an increase in tensile strength by 3 times. Such hardening is due to the grain refinement and formation of copper-contained nanoprecipitates at the grain boundaries. It was found that low temperature short-term annealing and small additional deformation leads to a good combination of high strength and high ductility with reasonable electrical conductivity. The obtained enhanced plasticity of aluminum copper zirconium alloy is kept in a wide range of strain rates and strongly decreases at higher strain rates. It was found that the value of strain rate sensitivity coefficient is not high and about the same in the both states of the UFG alloys, before and after the treatment annealing plus deformation. Hence, grain boundary sliding was concluded not to play a key role in the effect of plasticity increasing. The plastification effect can be explained within the model, according to which the increased plasticity is associated with the introduction of an additional extrinsic dislocation density in the grain boundary structure that facilitates formation of grain boundary dislocation, pile-ups, and emission of dislocations from grain boundaries under external loading. The diminishing of plastification effect at strain rate of more than 10 to the power of -2 reciprocal second is associated with lack of time for the formation of dislocation pile-ups at the grain boundaries during loading. There are some references. And that's all. Thanks for your attention.